Hello and welcome to BEZNext with thought leaders in modeling. Today our guest is Dr. Neil Gunther. Neil has a lot of experience in academia and IT. He published multiple books. He's the CEO of Performance Dynamics.
These days, business people and managers, people who are making decisions, IT decisions, okay, they think they have a lot of data, a lot of information characterizing business processes or characterizing behavior of computer systems, but they still complain. Having data, information, even prediction results is not enough to make decisions. And models are frequently used in order to justify different decisions. So what is the model? What is the purpose of the model? So we invited several expert industry leaders, thought leaders in modeling, to share their ideas about role of modeling, describe value of modeling, and share with us their thoughts about future of modeling. Today, we're happy to introduce Dr. Neil Gunther, and Neil is recognized industry leader in modeling, performance prediction. He's one of the first, his company, one of the first company which developed open source performance modeling software called Pretty Damn Quick. He developed several books. You can find a lot of information about Neil and Wikipedia. You can find five books written by Neil at Amazon. We'll talk with Neil about modeling. So what is the modeling? What is the modeling? What is the role of modeling, Neil, from your point of view, based on your experience?
So from my point of view, I think rather than talking about models in some abstract sense, I prefer to talk about a specific example. And the reason for that is because the word model itself, even within the context of performance analysis, that's to say computer system and network performance context, which is what we're going to talk about today, broadly speaking, IT, the word model, even in that context, is completely overloaded.
Yeah, I agree that having specific example really qualify the idea and help to understand.
Right. So in my classes, I actually hammer this point home because I've often heard presentations from people, including at CMG, where people use the word model and then they launch straight into the details of what they've done and how fantastic their model is, without ever telling us exactly what kind of modeling approach they're using. The audience is left to try and figure this out for themselves. Well, usually I could figure these things out fairly fast, so then often I ask the speaker, what kind of model are you talking about? Are you talking about a simulation? Are you talking about a queuing model? Are you talking about statistical regression? Or are you actually even talking about performance modeling at all? Yes, maybe you mentioned model meaning another thing, such as a model train set. Model can mean a model train set in English. It could mean a model like Kim Kardashian. That's another use of the word model. It's used in financial work in accounting. Every accounting department does modeling every day, usually in Excel. And by the way, nobody ever questions what they do. Whereas if you do it as a performance model of a computer system, nobody believes it, which is, of course, why we're having this discussion. So that's another issue. And then we have things like Amdahl's law, which is actually a form of model, but people don't necessarily think of it that way because it's an equation. But guess what? An equation is a model because it relates certain variables or performance metrics in our case. And we can go right down the list, numerical mesh simulation. That's what supercomputer people do, or particle physicists or astrophysicists use that kind of modeling technique. When people do load testing, such as using a tool like, say, Load Runner, for example, which is commonly discussed at CMG, it's usually never mentioned that what they're running is a model. It's a workload model. In fact, it's a form of simulation. It's a very expensive form of simulation because you actually have to set up a real system to run it. But nonetheless, it's a form of simulation. It's therefore a model because the people running the test and the people who receive the information or the data from the test believe, they never check this out, they believe that the representation on the test system is a faithful representation of how things are going to look in production.
Right.
Because we all know that, in general, that's almost never true. So the real question should be, well, how close is it? What is the level of accuracy and so forth? But and then we get into more modern context of modeling, where we have things like support vector machines and so on in the context of machine learning, and neural nets now are very popular.
Right.
And there we have another kind of a problem, which is kind of addressing your opening remarks, where people say they have a lot of data. Well, actually, to do machine learning, it's an absolute necessity that you have a lot of data. What's not important anymore is that you understand that data. In fact, that's the last thing people worry about anymore. Because what happens is they just pour, the buckets of data into the machine learning algorithm, and it decides what the model is. And in general, people don't know what that model is or what it means. They know it's a model, but they don't know why the machine has produced the outcome that it's produced, other than by comparing the output with some test cases. And when the test cases seem to match the arbitrary data that's fed into the model, there's a score, and if the score is high, then the model is considered to be good enough, and then they go and apply it to new data or random data at that point. But this is a problem because nobody really knows what's going on inside that black box where all this complicated monkey business is happening inside these machine learning models. Anyway, we're not going to talk about that today, but that's a whole other thing that's developed and has become a very hot topic just in the last few years, actually. And actually, I even have a student who tried to apply machine learning algorithms to the kind of performance data we're talking about today. And the results, I can tell you, were very mixed. So anyway, the main point at this stage of the discussion is that it's important that we define very clearly what kind of model we're talking about when we use that word model, because it's just a very generic term, doesn't tell you very much. So we need to refine and define the word model specifically. So that's what we're doing here.
Okay. So, and we're talking about performance models. Performance models, application performance models for informational technology, for IT.
That's right. And so what I'm trying to say here is that the performance model for me is a mathematical framework. That doesn't necessarily mean it's complicated. It can be a simple framework, as I'm going to show in this example. But it's a mathematical framework that's used to assess the validity of the collected performance data, whatever those sources may be. Now, the running assumption that a lot of people have in their head is that the data is the truth. And in my view, this is completely false, because actually all data is wrong by definition. But very few people understand that. What I mean by being wrong is that data is not mathematics. Data is a process of measurement, and all measurement has error in it. Therefore, all data is wrong because it's erroneous. The only real question is, how big is the error, and are you prepared to tolerate it? If not, then we need to change the measurement process. So that's the first important point, actually. And then the next step would be, given that we think that the data is a reasonable representation of the system in the sense that the measurement process is working, there's nothing broken in the measurement process, which has to be checked, then we can take our data and put it into a framework, and that framework is the model, and we compare the data in the context of the model, that framework. Why do we do that? Because that converts data, which is essentially meaningless, into information. The only way to get to information is to combine the data with a model. And depending on your actual context, leads you to choose different kinds of models. And I'm going to explain a very simple one here today, which we'll get to in the next set of slides. But that's the main objective, to combine data with a model in order to extract information so that our brain can understand what's going on. That's the goal.
So Neil,
Yes.
if data always wrong,
Yes.
it means model not necessarily accurate. Can we use not necessarily accurate model to make right conclusions?
Well, no, because they're generally going to have this garbage in, garbage out situation.
Okay.
So, but the reason I'm emphasizing that all data is wrong by definition is because most people don't think that way. what they usually think of, and this is particularly true of management, by the way, is they think that the model is the problem, because they think of the model as a kind of a crystal ball that's going to tell us something about the future as if by magic. And what I want to emphasize is that it's not a crystal ball. In fact, a crystal ball is just a worthless piece of glass. So we have to pay attention to the kind of model, the kind of framework that we choose. It has to be relevant to the kind of data that we're trying to analyze. And then we have two issues. One is the accuracy of the data, and the other one is the accuracy of the model. So both of these things have that question mark over them, and that's why it's so important to understand how accurate the data is, so that you can then eliminate any problems from the data source, and then accuracy will be to do with the model.
Okay.
So you can treat it as a process of elimination of error. It's not elimination, but you're trying to reduce the error as much as possible, and that's the best you're ever going to do.
Okay. So let's come back to modeling. Okay. So model has some limitations because data accuracy and because of different assumptions which we use in order to build the model, is that right?
That's right. So, for example, if you were using an equational type of model like Amdahl's law that I mentioned on the previous slide, well, there's not very much room to maneuver there. You've only got like basically one variable, one parameter. And if Amdahl's law is not an appropriate model for your data, then of course the model will appear to be making inaccurate predictions. But that's not because the model is wrong per se, it's because the selection of model is not appropriate for the context as represented in the data. Now, of course, this is the art of modeling. This is where expertise comes in, because it takes a lot of experience to be able to decide what is a good model. And, you know, that's a non-trivial process. Let me just make one more remark on the data side.
Okay.
On the data side, people have the idea that because they see the numbers on a computer screen or in a log file or something like that came from some kind of computer system, that somehow that data comes from God. It doesn't. It comes from the devil, because the data is, first of all, it has to be part of a measurement process, which involves some kind of measurement procedure or an instrumentation of some kind, which you may or may not know about. And then very often the metrics that you're looking at in the case of performance modeling is the metrics are constructed in software. And that software was put together by people. How do you know they put it together correctly? You don't. And what's worse is a lot of this stuff is, of course, done in software as code. And coders like to make improvements, and I use that in quotes. And sometimes, and I have very interesting examples of this in my class that I discuss, where people have introduced improvements, didn't tell their management, and then completely destroyed such things as customer benchmark to the tune of several $1 million. 10 million to be exact, in one case I'm thinking of. So the point is, I wasn't aware that the performance instrumentation, which I assumed was going to operate in a certain way, was now in fact broken until we came to run it in the context of a customer benchmark. And then I discovered things didn't seem to be right, but it took a long time to figure out why not. And the answer turned out to be that the engineer who wrote the code decided to make changes and not tell anybody, and he broke it. You see what I'm saying?
Right.
The way you can get a handle on this, actually, interestingly enough, is if you choose a model that's appropriate, then you can put a fairly high degree of trust in the model, such that if the data does not reconcile with the model, then the measurement process is broken. Not the model, the data. And I can tell you, chapter and verse, that's the most common situation.
Okay, great. Let's talk about example.
Okay. So, hang on. Don't you want to finish that slide? Because there's important points. So, having got to data plus model is equal information. So, you need to select performance metrics that are input, such as response time or service time or queue length, this kind of thing. And then you want to have a relationship between those metrics. That's the more important thing, not the metrics themselves, but the relationship between the metrics. And in every case in performance analysis, that relationship is non-linear.
Right.
Even if you don't understand what that means mathematically, non-linear means you can just forget about trying to guess the result. Forget about trying to guess as a prediction. You will get it wrong because the brain doesn't know how to do non-linear prediction. It only knows how to do linear extrapolation. So we take the outputs from the model, which have been calculated using our mathematical framework, and then we compare those calculated metrics with other measured metrics and see how well they match up. And if they don't match, we go around and repeat the exercise by either selecting different metrics or checking out the measurement process until things agree. And then, once we're satisfied with all that, we can then potentially make predictions about metric values in circumstances that weren't measured, i.e. the future, or in some cases about metrics that are not even measurable at this point in time. It may never be measured, but may be very important to know for other reasons, such as business decisions. So now I'm going to talk about a real simple but real example, and I don't want to go into all the details, but roughly speaking, we have a very big system, which happens to be a 200-node IBM cluster, and this was being used in the context of doing seismic analysis for oil. So it was actually an oil company in Houston, Texas, actually. And the data comes in from seismic measurements, both land and marine, they call it. So you remember what happened to the Gulf of Mexico a few years ago when one of the oil wells blew up. But the reason the oil well was in the middle of the Gulf of Mexico is because the seismic data had shown that there was oil there. So that data is captured on DAT tapes, small magnetic tapes, or at least was then. Maybe it's flash today, I'm not sure. And then actually use a mainframe to stage the data to put onto the IBM cluster. So in other words, this is a very complicated system, but the basic purpose of it is to run a set of applications that help the geophysicists to analyze the data for oil. That's what they're looking for. Texas tea, black gold. All right, so in this particular situation, it turned out that the applications, which were homegrown, by the way, at the oil company, they weren't purchased or they weren't from Microsoft or something like that. They were homegrown applications specific for geophysical application. The main problem, without going into too much detail, was that several of the applications could take up to a minute to launch. So that means just like you have an icon on your desktop, you click it with your mouse, and you expect the application to open up. That's what normally happens. You do not expect to have to wait up to a minute for it to open up. And yet that, in fact, was the circumstance. And I'm showing a set of data here in the form of a histogram, and you can see the spike sitting there. So there's one data sample where the spike up to 60 seconds to launch is very evident, and the other histograms represent, the variation in the launch times. Quite significant in themselves, even though they're not 60 seconds necessarily.
Yeah.
So the point is that management was frustrated by this, and also so were the geophysicists. And in fact, some of them were voting with their feet and quitting the company. And management was also, at that time, seriously considering removing the IBM cluster, which is a multi-million-dollar machine, and replacing it with some other vendor's hardware. So already we're talking about multi-million-dollar situation before we go any further. And then we have the added pressure that some people who are the experts in analyzing the data are actually quitting the company. So this is a real problem.
Yeah.
So both cost and the whole line of business was in jeopardy, actually. So here's just a small sample set of data, just focusing in on the basic results that I got after several months of work. And it shows that certain kinds of servers, which I'll explain in a second, shown in the left-hand column of the table. And each of those servers has a different number of files shown in the middle column of the table. That represents the number of files. And then the third column shows the time it took to launch from each of those different servers. And you can see that roughly speaking, the launch time is then somehow related to the number of files sitting on the server. The more files you have, the longer it takes, basically. Now, in the bottom of the slide, I'm showing that you can go one step further. Numbers like 100 are very close to 128. So 109 is very close to 128. 4,781 is very close to 4096. 8,371 is pretty close to 8,192. Those are all powers of 2. So this tells you immediately that the launch time appears to be related as the logarithm, that's to say the exponent, of the number of files in base 2. Now, that's just one way of saying it. You could also do it in base 10, but base 2 makes it pretty obvious here in this case. So my observation was that if I take the number of files and take the logarithm of that number, it would give me a number that's very close to the actual launch time expected. So in that sense, I'm making a prediction, if you like. But now, this is just in the beginnings of putting a model together, so now I have to try to validate the model. And you can see that if I plot this as a log linear plot, that's to say the data, there's 4 or 5 data points there, I can fit that with a straight line. That tells me that, in fact, the idea that it's logarithmic scaling must be correct, because that's a pretty good fit. We can check that again by plotting it as the actual logarithm, and you can see that the curve, the blue curve, which is the logarithmic curve, goes through the data points near enough. You know, this is statistical regression, so that's good enough. So this is the first hint that this is a good approach. So having analyzed the data, which by the way I collected for myself, because the data that was necessary wasn't being collected by a standard set of tools like commercial performance tools, but I'm not going into those details here. And what I'm proposing as a hypothesis, if you will, the model is that the launch time is directly proportional to the logarithm of the number of files on the server. Now, if I change from base 2 to base 10, the number happens to be 4.57. And if I plug that value into the model and go back to the original table, I have now that the servers as you saw them before, the measured launch times, and the launch time predicted by my model, which just happens to be the equation in the blue box above. And you can see then, if I calculate the standard error, it's within 5%. This tells me that my simple logarithmic model, let's call it, explains what's going on to the tune of 95%. The 5% is noise, which I don't have to worry about. So the model's accurate within 5%. So this gives me a high degree of confidence that I understand the relationship between the number of files and the launch time. That's a relationship that was completely and utterly unknown to anybody in the company until this time when I came up with the model. But the remaining question that this raises now is, where is this logarithmic behavior coming from? Well, it took me a little while, but actually it took me lunchtime to figure this out. But I remembered an old adage, which is to get a log, you need a tree. So imagine these files are arranged as usual in a directory format, as they usually are on a computer. And we can think of that directory structure as being like an inverted tree. The depth of the tree is logarithmic. So I've shown it here for base 10. So we have 1 at the root of the tree, the top of the tree, because it's upside down. So the root of the tree is 1. Well, that's 10 to the power 0. The next level down would be, say, 10. Well, that's 10 to the power 1. So first level is 10. Second level, that's 10 to the power 2, which is 100. And you can see the 100 arises from 10 times 10 branches. That's the logarithmic behavior. So the logarithmic behavior for the launch time is associated with the number of files according to the model. And the reason for that, which is not evident in the equation, is because it's to do with the fact that the files are organized as an inverted tree. And the depth of the tree is logarithmic. So these are the modeling results. So as I said, management was considering replacing a multi-million-dollar IBM cluster. And because of the model that I've just shown you, I could say with 100% confidence that that would have been a terrible thing to do, because if they had, first of all, scrapped the IBM machine, which is already, they spent multiple millions of dollars on, and then spend more millions of dollars on a new machine, whatever that might be, he would have achieved nothing. And it certainly wouldn't have solved the launch time problem, not at all.
Right.
So the point being, and we don't have time to get into all this today, the point being that the actual machine that I called the server was actually serving up fonts. The files are font files, fonts used to draw windows and images on the computer screen. And the servers were completely separate from the cluster. And if they had to replace the IBM machine with a SGI or Sun Microsystems or whatever, they would have still been using the same original source machines for the font files, and that would have achieved nothing.
Right.
And the other thing I think is very important to stress here is that this problem was caused by adhering to best practices for system management. In other words, in my view, as far as I've discussed the problem today, nobody was doing anything wrong from a system management point of view. On the other hand, performance management was completely overlooked.
Right.
Because it wasn't part of so-called best practices. And
So every time they open the file, it takes some time, use resources. More files you open, more resources you use. Is it right?
well, actually, it's a lot more complicated than that, which we really can't get into this because it's too complicated. But
okay.
it's partly to do with the fact that the fonts that it's looking for, it's not making, the application is not making it's a remote font server. The application is not making a request for a specific font. Say, for example, Courier 12. It's not doing that. It's saying, I have this window as a certain geometry. Please give me the best font that matches that geometry. Keyword being match. Now, the font server has to go and rummage into the basement, go down the tree, not to find a font, but to find the best matching font.
Mm-hmm.
Well, this is costly. It's going down the tree that's costing the time. It's costing logarithmically.
Mm-hmm.
On the other hand, the reason that this didn't show up all the time, notice it was a spike of 60 seconds amongst a lot of other spikes which were much lower than that. The reason is because the font servers also cache previously used fonts in memory,
Mm-hmm.
and therefore can look in memory sometimes, and that's faster. But every now and then, the fonts that are needed that match the best won't be in memory. Now the font server has to go and rummage down the tree again.
Okay.
That's why it was sporadic, and why it's not easily predictable. But the
And by the way,
is accounted for by the logarithmic model.
And by the way, we're talking right now about basically retrieving opening files. We're not talking about running application itself. It will happen after that, is it right?
Yes, well, yes. So, yes, after the 60 seconds or whatever the time happens to be, then the application will continue and then eventually display on the screen.
Right.
That's correct. But until such time, it's held up.
Right.
It's held hostage by the font server. But I'll say it once again. Nobody was doing anything wrong, and when you have a 200-node cluster like that, the better thing to do is to have a remote font server. There was a single source for the fonts that distributes across all of the 200 nodes, rather than putting copies onto each of the nodes. You could do that, but that's much harder to manage.
So in this example,
font server is the correct thing to do.
Yeah. So Neil, in this example, you demonstrate that even simple model help to avoid unnecessary upgrade.
Well, it's not upgrades, it's completely scrapping one machine and buying a whole new machine, which would have achieved nothing.
Okay.
To the tune of, multi-million dollars 2 times over, at least.
Mm-hmm.
I mean, this would have been an absolute disaster.
Yeah.
Absolute disaster.
So what is the value of modeling here?
Well, you can look at it different ways. I mean, one of them is multiple millions of dollars were saved.
Okay.
Probably quite a lot of management jobs were saved because there would have been a lot of heads rolled if they had made the decision to replace the hardware.
Okay.
And so the performance management was completely overlooked. and you've got the idea, I think, from what I've said, the font servers held 15,000 font files. If you go back to the table and add up the fonts, it turns out to be about 15,000 fonts, which is just accrued over time by installing each revision of the fonts with each new release of the software in the way that you're supposed to do according to system management procedure. It's completely correct. On the other hand, you're killing the scalability by doing that. But nobody did the performance analysis, so they didn't know that. What I discovered was you only need about 1,000 fonts at most. And the simple logarithmic performance model tells the whole story. How can I say that? Because it's correct up to 95%.
Right.
And that also told me that the fix was very simple. Just prune the tree. In other words, reduce, scale back the number of fonts. They only became that big because you improved them by just doing the system management thing. Now go back and prune the tree, cost basically nothing. There's no CapEx expenditure. No hardware needs to be replaced. And you get a 300% performance win, which is exactly what happened and exactly what I proved to be correct.
Yeah. Okay. So if you generalize your experience here in everything that you're showing and think about value of modeling and future of modeling, okay, what are your thoughts about that?
Well, so the last point is very important. That this particular kind of performance model, this log model, I'll call it, it was really more about explanation than it was about prediction. The prediction was almost the least of it. I mean, it obviously has some predictive power because it told me, once I realized that the logarithmic behavior was coming from the directory structure on the remote font server, it's pretty obvious that what you need to do is prune the tree. So it tells you to do, it almost tells you to do that. Pretty obvious. And so that's predictive, but the real point or the real value of the model in my mind was that it was explanatory, not predictive, explanatory. And that's another very important reason to construct models, is to have a solid framework which provides an explanation of what is going on, because once you have that explanation in hand, you are less likely to recreate the same problem again in the future, because you understand now something you never understood before. And actually, in this particular case, because those font servers actually were in a closet with the lights out somewhere else on the network, nobody even really knew about it. So it was out of sight, out of mind. But the performance model revealed, with a lot of work, the performance model revealed what the culprit was and what should be done about it. Because it provided an explanation.
Okay. But
which in my mind is different from forecasting.
Okay. Okay. And if you talk about, let's say, future application of modeling, okay, for different purposes, what are your thoughts? I know that you're a proponent of the simple models. Even simple models frequently provide a lot of value. Even not necessarily 100% accurate model, they can provide value. Okay, so even we discussed at the beginning that data is not necessarily accurate. At the same time, we're able to find approximation, logarithmic approximation, and find some useful results. But in industry, what are your thoughts about what are your forecasting predictions? What will happen with modeling? Will people use continuous modeling? What is the best application of modeling for information technology? What do you think?
Well, first thing I'm going to say is that, going back to a point you just made, no model is 100% accurate. Actually, getting a model that's 95% accurate is extremely good, it turns out. And as the statistician George Box once said, or I like to paraphrase what he said, the way I like to say it is all models are wrong. Just like data, all models are wrong, but some are wronger than others.
Right.
I think he said some are better than others. But the point is that you never have 100% accuracy, either from data or the model. That's not the nature of the game at all.
Right.
The nature of the game is what level of inaccuracy can you tolerate?
Right.
And to be able to answer that question already implies that you have a fairly good understanding of what it is you're doing. Otherwise, you can't even answer that question. As regards to future of modeling, well, first of all, I think we have to go back to the first slide. What models are you talking about here? to me, there's a spectrum of models, or panoply of models, and I don't think any of those models are going away. I mean, in some sense, what I'm doing here in this example could have been done on a mainframe. It could have been done 40, 50 years ago. Same thing. We didn't typically have remote font servers back then, but it could have been a similar kind of circumstance where one machine was talking to another, and you could have had that kind of a latency. And this model would have been the right kind of thing to do even then. I mean, in some sense, the models are technology independent, in my view. So that, I don't think it depends on the context. There's all different kinds of models you can use, as I listed in the beginning of the slides here. I don't think any of those are going away. And as I also hinted at in the beginning, one thing that has changed or is changing is the word model has taken on a new meaning in certain domains. And the domain I'm talking about now is generally called AI, artificial intelligence.
Okay.
Which is not a particularly good term because that's also completely overloaded, and it's been a dream since the 1950s, which still hasn't been realized. But nonetheless, from a technical point of view, there is a lot of progress being made in certain areas, in certain domains, such as, for example, image recognition, and in particular, image recognition in the medical field. So it's now provable, I'd say we have quite a lot of evidence that artificial intelligence type models, by which I mean machine learning or deep learning, convolutional networks and so on, are able to achieve results in terms of identifying such things as, say, tumors better than a human. In other words, with a higher hit rate than a human can do. So this is an interesting circumstance because on the one hand, the machine seems to be doing better under certain circumstances than a human can do visually. So that's already interesting. And the scores and the data are there to support that. So I'd say we definitely have evidence for that. I wouldn't dispute that for a minute. What is a little bit troubling is that we don't know what those models are in any real detail. We're kind of trusting the machine to have produced a good score and do things accurately, but we don't really know what the model is or why the model parameters have the values that they have. In that sense, we've relinquished a certain amount of control. And by that, I mean we've relinquished a certain amount of understanding, and that bothers me a bit.
Mm-hmm.
It may turn out that in the future, we get a better understanding of what the machine's doing, and then we're able to address the question of why the parameter values are the way they are.
Okay.
That's not completely clear to me, but that could happen. But at the moment, I think that's a little bit troubling. And the other thing is that people, of course, because this is a hot topic, people tend to be getting the impression that the kind of modeling that we've been discussing today is a bit old-fashioned. And I would dispute that. It may be old-fashioned, but that doesn't mean it's not useful. Well, modeling is a framework in which to validate data.
Okay.
You need to validate the data in order to get from data to information. Data is not information. You need a model to get to information.
Okay.
And the reason you want that information is to be able to make cost-effective decisions.
Okay. Okay.
And I've tried to give an example where the model is surprisingly simple.
Mm-hmm.
On the other hand, I think you can agree that it was incredibly powerful and effective. And you mentioned my physics background earlier. In theoretical physics, we always choose the model that is the simplest.
Mm-hmm.
I said it very nicely. He said, the model should be as simple as possible, but no simpler.
Okay.
Well, that's the same. It's exactly the same goal in performance analysis or performance modeling, and strictly speaking, it should be the case in every domain where modeling is being done.
Okay.
just going back to your question where you asked me about the future of modeling.
Right.
That's a bit of a, I don't know how to address that, but one of the things that I heard at the Informs conference in Canada last week or the week before was that on the upside of computing, what they were talking about doing optimization problems, of course, convex hull, that kind of thing, involved with decision making for real situations. And one of the things that pointed out was that if you go back about 20 years, the kinds of problems that could be solved using linear programming, for example, which is complex hulls and all that kind of stuff, you could program it, but you could only solve models which had, let's say, relatively few parameters in them. Today, with modern computing power, they now claim that they can solve linear programming problems with hundreds of thousands of parameters in them. In other words, almost any problem can be attacked that way. Any problem in that particular domain can be attacked because of the compute power. And there's a certain similarity between that and this whole business of AI and deep learning, because in both cases, in a sense, we've given up the idea of understanding what the model is. We kind of program it, and we hope we've done the right thing, and then we let the computer do the computing, and we take the result and we try to assess whether it looks valid or not. And at some point, you just give up and say that looks good enough. But in terms of your complete understanding, how do you completely understand a model with hundreds of thousands of parameters? You don't. So I guess in a sense, you could put the machine learning problems and the the modern linear programming types of problems are kind of in the same camp from that point of view. We can solve very complex problems now, but we give up a little bit on the insight side of things.
Okay.
And I'm just saying, I would caution you don't want to go too far in that direction.
Okay, Neil, thank you very much.